don't have to draw all the diagrams down and everything. This section it probably won't be that bad for you. It's one central idea that's called linear approximation. Okay, I'll put this up there at break. I'll go ahead and do that so I don't forget. Okay, so just pay attention to the diagrams. You don't have to write them down. So here's kind of what we're doing and what we use linear approximation for. Before I show you what it is, let me just give you sort of an idea, okay, a rough idea. Okay, have you ever wondered how somebody figures out the square root of 26? No, it's never occurred to you, never interested you at all. Okay, there are several ways. Back in history, there's something called Newton's method that you can do. We used to teach this, years ago, how you find square roots of numbers that are not perfect squares. Well, calculus can be used to approximate it, okay? And your calculator, of course, does that. There's something going on behind the scenes with that. What's going on behind the scenes generally is something called a series, which you learn about in calculus 2. That's how it's generating decimals of pi also. There's something called an infinite series going on. So this is kind of getting you prepared in some way for Calc 2 when you learn about infinite series. So we're going to learn how to approximate something like that. Another example would be cosine of 29 degrees. Okay, you can use calculus to approximate that value, within an accuracy of maybe 1% or 0.5% or something like that. So that's what we're ultimately going to get at in this problem. So the calculus behind this is kind of saying this. Okay, so if you have a function, like this is a function, and you know about tangent lines, if you continued to zoom in on your calculator on a tangent line, what would eventually happen is, wouldn't that tangent line just almost look like it's exactly like the curve? In other words, if you zoomed in on a curve, it would eventually start looking a whole lot like a line. Do you agree? I mean, that's as microscopically you go in there, it's going to keep eventually it's going to be, you wouldn't even be able to distinguish between the tangent line and the curve. Does that make sense? Okay. And same thing would happen if you had a corner, like what we call a cusp. If you kept magnifying that, the cusp would never change. It's still a cusp. Okay. So the idea with a linear approximation is you're going to kind of have a diagram kind of like this. So you want to draw this diagram on like this. So we have x and f of x. This is what you want to draw down here. So let's say that you have some sort of a function. Let's say that it's something like that. Let's draw something kind of like that. That's f of x. Okay? And let's say that we're interested in, let's put like a dot there. And if we go straight down there, we're going to call that a. Okay, a just represents some number, okay, some x value. You can write that if you want to as x equals a, okay? And then, of course, what this is going to do is this is going to give you the function value, so that would be f of a, okay? You know that already. Now, what we're going to do is we're going to do a tangent line to this, so the next thing that you want to do is just kind of just approximate a tangent line kind of like that or something, okay? It doesn't have to be perfect, just kind of approximate it like that. Now what we're going to do on this is we're going to represent this as, of course, that's f prime of x, right? That's your tangent line. So what happens on this then is if you moved over a little bit bigger on this, okay, if you went to a little bit bigger value, like you could say this is x equals a plus h or something like that, where h is just a small value, then if you went all the way up to that derivative, okay, then if you evaluated that derivative, okay, the value f prime of that value right there is going to be pretty close to that function value right there, okay? They're off a little bit, so the idea is if you did f prime of a plus h, okay, that function value would be pretty close to f of a. Okay, agree with that? Now the thing with h is we could make it small if we wanted to like that. So if we made that smaller, then those things kind of close in. So it's kind of like what we think about when we're talking about with a derivative. So the idea with a linear approximation is what we try to do is we use the derivative to approximate that function value. And ultimately what we're going to look at is stuff like the square root of 26, where you look at the square root of x, you can graph that function, and then you can approximate, you can compare that to the square root of 25, and you can use the derivative to get that extra piece right there. And it'll make a lot more sense when I do a specific concrete example. So that's the idea. So what's going to happen is that derivative, if you move out a little bit, that derivative is close to approximating that function value, okay? All right, so what we want to do with this is let's go ahead and do this approximation of 26, just kind of using a linear approximation method. Okay, so what we're going to do is let's go ahead and let's do the square root of x, like that. So we're going to graph that function, okay? Because we're doing a square root function. If you were approximating a cube root of something, you'd use a cube root function and so forth. Okay, so if you plotted this, now let's just get some specific values. Let's go all the way out to at least 25. So let's say that this is 25. Let's just go like this, 5, 10, 15, 20, 25, 30, or something kind of like that. I'm going to do that a little bit better. Okay, so I'm going to do like 5, 10, 15, 20, 25, then all the way out to 30 like that. Now what we're going to do is we're just going to approximate values. So like the square root of 25, of course, is 5. So we need to make our y-axis go up to around 5, at least 5. Okay, and then we're just going to plot some functions. You can do all this in your head. The square root of 25 is 5, so you have that. Okay, what's something else you know? You know the square root of 16 is 4. So if you go over to 16, you would go up to 4 like that. Another one you know is the square root of 9 is 3. So if you go over to 9, right about there, you're up 3. The square root of 4 is 2. So if you go over 4, you would be up 2. And the last one you have square root of 1 is 1. So you'd be kind of in there. And the square root of 0 is 0. So I'm just getting some accurate points when I do that. Okay, so that's going to be what the graph of f of x equals square root of x is. Okay, so that's what I'm doing so far. Okay, so what we're going to do when we do a linear approximation, what we end up doing is, and it's going to end up being kind of like, we're going to develop a formula for that. So what we're going to do on this is, let's go ahead and do this. So let's draw like a line down like that, and then over like that. Okay, so what we have is we have the square root of 25 is 5. Now what we're going to do is go to 26 though. So let's put in like a 26. So what we're going to do is go up to the curve, and that's going to be a little bit bigger y value, only a little bit bigger. So we're going to kind of go over like that. So what we're trying to do ultimately is we're trying to find what f of 26 is. You would expect it to be 25 point something, okay, just a little bit bigger, okay? So the idea, what you end up doing on this, and I'm going to show you how this goes. I'm going to give you the formula and kind of show you how this goes. So the linear approximation, and you want to write down the formula. I think I put the formula down here on this, down like this. So that's the formula, and I'll show you how you remember this. It's going to be f of a, okay, then you're going to do f prime of x, or f prime of a, like this, and then x minus a. So let's go ahead and get that written down, and I'll show you where that derivation comes from. Okay, you've actually already learned this formula before, but you might not recognize it yet. Okay, so here's what we end up doing in this problem. You want to try to make sense of this. Okay, first of all, what you're doing, when you're doing f of a is going to be that piece right at what you have right there. Okay, now that's going to be, you're comparing it to something you know. You know the square root of 25, right? So then what you would do, so this part right here would be f of 25. This little tiny slice right here, that little piece right there is going to be the f prime of a, or the f prime of 25, and then it's going to be times 25, and then you're going to use 26 minus 1, so that's just going to be 1. So what you need to kind of understand on this is, and I'll derive the formula, what you're doing with this is you're taking the function value of 25, which is 5, and then this piece right here kind of gives you that extra amount, like that. So it goes like this. With the reason you use the derivative on this is if you did the derivative at 25, like this, I'm going to try to draw my tangent line right there, what you would end up having is this part right here would be the x minus a part, okay? And then this part right here, the f prime, would end up being this value right in here. So if you multiply those two things out, you're going to end up getting that extra little piece right there. Okay, that's kind of the idea. Now let me go ahead and crunch it out, and once I crunch it out, I'll go back and I think you'll see specifically how this works geometrically, okay? And this formula comes from here, by the way. If you did this, if you move this f of a to the other side, you would have L minus f of a is equal to f prime of a times x minus a. Does that look like any formula that you've learned this semester? I'm curious, because you have learned this formula. How about if I write it this way? L is a y value. That's the linear approximation. That's a y value. That would be whatever the square root of 26 is. Ah, there you go. It's point slope. Good. Okay. So that would be like, and that should be an f of a right there. F of a is also a y value. Okay, that's the slope. F prime of x is the slope. A is really an x value. Okay, linear approximation formula is the point slope formula. That's what it is. What you do is you just move that over to that side and you get that. Okay, so let's go ahead and let's crunch this out now, and then I think the geometry will make more sense once you see that. So here's what we're going to do. We're doing a linear approximation for 26. Okay, so what we do on this is we're going to go ahead and let A be 25. Why 25? Because we know the square root of 25, right? And that's close to 26. That's why I'm doing this. So that's going to be, f of a is going to be just the square root of 25. Okay? Then we go over here, we're going to do f prime of 25. And then over here, we're going to do the 26. And then a is going to be 25 like that. So if we do that, a calculation, we should get something that's a little bit bigger than 25. Okay, so let's go ahead and do that then. Okay, so the square root of 25 is going to be 5. So we're going to do that. Now when we do the derivative, now remember what we're doing is we're doing the derivative of that function. Okay, so let's go ahead and do the derivative of that function. That would be f of x is 1/2, or is x to the 1/2. So let's do that. Then f prime of x is going to be 1/2 x to the negative 1/2 like that. Okay, so that's going to be 1 over 2 x to the 1/2, or 1 over 2 times the square root of 20, I'm getting ahead of myself, 1 over 2 times square root of x. Okay, so that's the derivative. And then you got to do that like you would do in the point slope formula. Okay, so what you're going to have here then is when you do f prime of 25, you're doing 1 over 2 times the square root of 25, like that. And then, of course, 26 minus 25 is 1, like that. Now, what we want to do is we want to go ahead and use our calculator to crunch that out. So when you do the f prime of 25, you're doing the derivative and evaluating that like that. So what you're going to get here, when you do this, is you're going to get, bring down the 5, so you'll have 5 plus, you should be able to do that in your head. That's 1 over 2 times 5, right? So is that 1/10? Okay, right? 2 times 5 is 10. Times 1 would be 1/10. So the answer is 5 1/10, which is about 5.1. So that would be what we call the linear approximation for the square root of 26. Well, let's see how accurate we are, just out of curiosity. So if I did the square root of 26, let's see what we get. 5.1, almost, okay? So what this linear approximation does is it can get you accurate within maybe a decimal or two. And it all depends on the curvature of the graph, like that. So what I'm going to do is kind of explain what this diagram was doing. See, this 0.1, if you look at the diagram right there, that 1/10 was that little piece right there. So the square root of 25 is this part. That's the f of a, like this. This part right here is that estimation. You add that to the 25 to get that. And what you're doing is you're really doing this. Now, I'll see if this makes any sense to you. This is, really what this is giving is that's a rise. And then that right there is really given a run. Okay, so what you're doing is you're doing like the slope of the tangent line. And the slope of a line is a rise over a run. So what you're really doing on this is you're going up by this value. So if you look at this right here, that tangent line, you're going up and over. The rise is 1. Everybody agree with that? Because you're going from 25 to 26. The rise is going to be approximated by that derivative. Okay, and it's an approximation. So the derivative is the value of that, the rise on that. So that's it. Now that's pretty abstract, but that's the idea. Okay, when you do this, it's not a hard thing to do because you're going to follow this formula specifically, and crunching that out's not hard. Trust me. It's kind of abstract with what you're doing this diagram, but you try to think of it as you're taking a function value and then you're adding on really what that slope is. Okay, so it's like that. Okay, so let's kind of look at, in general, some examples. So I'm not going to derive this. I'm going to go ahead and just show you how we use this linear approximating formula. Now, one other thing that you might want to write down on this, because this will help you remember this formula, is you already know the point slope formula. So I'm going to do this one more time. If you moved this over, you would get L of x. What does L stand for in this problem? That's the approximation, right? Of whatever we're approximating, that's what that is. Okay, then what you're going to do is if you move over the f of a like this, then that's going to be f prime of a times x minus a. Well, really what you get is this is just like the y value. That's the y value of your linear approximation. This is another y value. That's y1. Okay, this right here, you know a derivative's a slope, right? It's a slope of a line, so that's m. And then the a is going to be like x1. So see, it's all there. Does that make sense? The linear approximation formula is the point slope formula. It is. Okay? If you solve it for y, then you get that formula. You get what you want. That's the easiest way to remember that. Okay, let's go on. Let's do some problems. And it'll start making a little bit more sense once we get into this. So what this diagram does is this shows a little bit better than what I was drawing on here, is if you're doing a linear approximation, then you're finding f of a, so you're finding that piece right there, and then you're finding that extra value. This part right here is the extra value that you're doing. That's what you add to that function value. Okay, so let's do some specific examples. There's not too many I'm going to show you. I just want to get you comfortable with how to use the formula. Okay, so let's do this example right here. There's your linear approximation formula. So what we're going to do with this one is you're given a function and then you're given a point f of 2.1. What we're going to do is estimate what the function value of 2.1 is on this quadratic. You can find it specifically with or without a calculator, but we're going to do a linear approximation. Okay, so what we're going to do is write the equation of the line that represents the linear approximation. So you're really following this formula right here, okay, which is the point slope formula. All right, so what you have to do in this particular problem, first of all, a is equal to 2. So in this formula, you're going to use a is 2. And then what you need to do is you need to find the derivative. Okay, x is going to be that value that you're interested in right there. So x is 2.1. All you guys need to write down is the function I've given you. 12 minus x squared, a equals 2f of 2.1. That's all you need to write down. Okay. Now we just crunch it out. Okay, so what we're going to have is, first thing we need to do is we've got a is 2, we have x is 2.1. You want to find the derivative, so you want to work that out. Okay, so let's go ahead and do the derivative. Okay, this is the easy part of the problem. Tell me what the derivative of 12 minus x squared is.
Negative 2x.
Negative 2x, good. Okay, now we need to do f prime of a, so a is 2. Okay, so that's going to be negative 2 times 2 So f prime of 2 is going to be negative 4. Okay, so we have that. Now we have everything that we need to know in the problem. Okay, well, let's write down the formula. So we're doing L of x is equal to f of a plus f prime of a times x minus a. Okay, let's see if we've got everything. So let's see, we definitely have a. We have what we need there. We have x. We got what we need there. We've got the derivative. Okay, we got one other thing we need to know, and that is what is f of a. Okay, well, a is 2, so we're going to do f of 2. Okay, how do you find f of 2? You just take the function I gave you and you plug in. So that's going to be 12 minus 2 to the second. That's 12 minus 4. So that's going to be equal to 8, like that. So right now I'm doing stuff that you're familiar with. And putting the whole thing together is what the new thing is. Okay, so now let's put what we have. So L of x, that is like, and you can think of that, if you want to just write that as y, you can, because we're finding an equation of a line. So it's going to be like y equals mx plus b. Okay, f of a, what did we figure out f of a is? 8. Okay, that's the function value. Okay, how about f prime of a? What was that? That was negative 4. Okay, so that's going to be negative 4. And then x is just a general variable on that, so that's going to be our variable. And then a was 2, like that. Okay, so that's what we want to do on that. And we're not ready to do anything with the 2.1 yet. We're just getting an equation of a line. Okay, all right, is everybody following what I'm doing so far? Okay, so what we have is, you would have, it looks like you would have y equals 8 minus 4x plus 8. So that would give y equals negative 4x plus 16. And what this is really doing is this gives you an equation of a tangent line at x equals 2. You already know how to do that. I mean, you could even do this problem the old-fashioned way if you wanted to. If you wanted to just write down y minus y1 equals m times x minus x1, you would get the same answer. You see what I mean? So you're welcome to do it that way if you want to. All right? So that would be what you get for your answer on part A would be this. That is your result. That's the equation of the general tangent line. And we're going to use that to approximate the function. Okay? Now, what I've done here, I went ahead and just did this on the graphing calculator. And let's go ahead and just do this together so you can kind of follow along what I'm wanting you to do here. I think you'll see this a little bit better if you do this on your own calculator. Okay, so what we're going to do is let's graph the function. The graph of the function we're doing is 12 minus x squared. So we're going to do that. And while we're at it, let's put in the tangent line also. So the tangent line was negative 4x plus 16. Okay, so you're going to draw a graph, and let's just do this. Let's use the window that I have right here on my screen here. So let's just go to the window, and let's put in window negative 5 to 5. And this should give us a pretty good looking graph. Scale of 1, and then the y's, let's go 0 to 15, maybe by a scale of 5. Okay, because I want to show you a couple of things that happen on this problem. Okay, that's the quadratic. That's what you would expect. Then this is your tangent line. Now, what we were doing was we were finding the equation of the tangent line at 2. So let's do this also. If you trace it 2, does that look like that's a correct tangent line? What do you think? Yeah, see, that's stuff we've done throughout the semester. So at this stage, I hadn't really done anything new, like I've said. Now, what you're going to do is you're going to approximate what the value of f of 2.1 is. So that would be the graph. You can sketch a graph like that if you want to. It doesn't have to be perfect and everything. You just kind of to get the idea, you might want to just label that's 5, that's negative 5. This is, I think, that was 15. And then this function is y equals 12 minus x squared. And then the graph of the tangent line was y equals negative 4x plus 16. Okay, so what I'm going to do is two things to kind of finish this up. In part C, what it says is use the linear approximation to estimate the given function value. So we're actually going to do L of 2.1. Okay, and all that means is we're going to take the graph of this tangent line, That's your linear approximation, and you're going to plug in a 2.1. So it turns out if you do the graph of the equation of the tangent line at 2, then if you plug in 2.1, you're pretty close. Okay, so if you do that, there's two ways to do this. You could do this on your calculator like this, or you could just trace out on the graph. So I'm going to do -4 times 2.1, and then add 16 to it. And that will give me about 7.6. So that's approximated by 7.6. Okay? Now you guys need to make sense of what I'm doing in this problem. Okay? Now what I'm going to do on this is show you another way you could do this. Now you could trace. I want to do two things. If I do trace, and you want to be on the line, different calculators do this different ways. You've got to go through and kind of toggle through. So if you traced on that tangent line at 2.1, okay, what that's going to do is that's going to give the 7.6. Okay? Now look what happens if I traced at the function. Okay, if I trace on the parabola and I type in a 2.1, let's see how close we are to 7.6. We got 7.59. See, we're close. And generally when you do these problems, your accuracy is, depending on what value you're doing, you're going to be relatively close. Okay, does that make sense? See, what I'm doing is that tangent line is going to have a very similar value to the function value of 2. You're comparing the function value of 2 to the value on the tangent line, or I'm sorry, the function value at 2.1 is being compared to the value on the tangent line at 2. That's what you're doing. Does that make any sense? Okay, it's kind of abstract. Okay, it's not hard. The calculations are not that hard, but that's the idea. All right? Okay, now we're going to do one more thing. We're going to do an error with approximation. Okay, so when you do an error, if you're going to take Calc 2 in the future, you're going to work with errors. We're doing this right now in Calc 2 with what we call series. So what you do is you just do this, and I think the formula's been given on here. What you do is you do like the approximate answer. This is the approximate or the estimate. Okay, let's just write that as the estimate minus the exact. And then what you do is you compare that to the exact. And you just do the absolute value because you want to get a positive value like this. Okay, so here's what you're going to do. Okay, the estimate was this right here. Okay, that's the 7.6. Okay, the exact answer was what I got on the calculator. If you did f of 2.1, you're really doing 12 minus 2.1 squared. Okay, because you're evaluating the function. I did that on the calculator, and we got I think that was, if I remember right, that was 7.56. Okay, all right, so that goes there, and then we divide by that exact like that. All right, so that's what we're going to do. The estimate's what I got. The exact is what you would get if you did just plugged in 2.1 into the function. So let's do that, and this will tell you how close you are in your approximation. Okay, so let's see what we get here. So I'm going to do 7.6. I'll just do this all on the calculator. Minus 7.56, like that. Okay, that's going to be 0.04. And then take the 0.04 divided by the 7.56. Then we want to change this to a percentage. So I'm going to go ahead and do that. That's going to give you a ratio. So that's going to give about 0.00529100053. You don't need all those decimals. Now, that's not a percent. What do you do to change something to a percent? What do you do at the decimal? Multiply by 100, or just move it over 2. So if you did that, you would have about 0.529%. So that's how close your approximation is, which is a pretty good approximation. Okay? This stuff right here, a lot of times students are saying, well, if I want to find f of 2.1, why don't I just do this? Well, sure, that's how you get the exact answer. Part of what we're doing is leading up to the idea in more advanced math, particularly in Calc 2, of how you do series approximations and stuff like that. So it's, in part, this helps you if you're going to go to Calc 2, just to have a little bit of a background for that. So that's kind of what you're going to be doing in the problem, is This is a good kind of classic problem. You get an equation of a tangent line, which is what that linear approximation is, and then you're doing an error estimation like that. Tell me if that makes any sense, or at least the mechanics of what I did. Okay? We'll kind of get into what the geometry means on that in just a little bit before we finish up class today. Okay, let's go ahead and approximation is. I think it will. At least that's the plan, okay? All right, so what you're really getting on this is, okay, your goal would be to figure out what the function value is at some point, okay? In other words, your goal on linear approximation is to approximate what that value is there. That's what you're trying to do. You're going to be close to that value. So what you do with a linear approximation is you look at some other point that's usually a little bit less than x1 over here. And like when we did square root of 26, what we use? We use 25 instead of 26, right? Okay? So you want to use a value that's pretty close to it. Well, okay, here's what happens. Okay, we're trying to get this value. F of A is not the same value, agreed? Okay, but we can use that to approximate that. So what we said we were doing on this is we basically want to find the equation of the tangent line at that point. Okay, and you can use y minus y1 equals m times x minus x1 if you want to, because that's what that formula is anyway. That's what you need to understand. So the idea would be this. If you got a function value on this equation of a tangent line, you would be there, wouldn't you? The function value on that tangent line is there. So that's fairly close, isn't it? So what you're trying to do is the error on this is going to be the difference between those two things right there. So what you're trying to do is when you get out to that point, that tangent line is close to that function value. Does that make any sense? Okay, and how do you find the equation of a tangent line? Well, you got to do the derivative, number one, to find the slope of the tangent line, which is what that is. Then you do x minus a, because that's just like x minus x1. And then that's like the y, and that's the y1 like that. So that's the idea. Does that make any sense? Okay, diagram-wise, you're looking at trying to figure out that point on the function, on the tangent line, to approximate that. Okay, sometimes it's close, sometimes it isn't. Okay. It kind of depends a lot on the curvature of that graph. Does that help any? Getting a lot of blank faces.
It helps.
Okay. All right. When you're punching these things out and crunching them out, it's not hard to do this, but try to wrap your head around that diagram. That'll help you a little bit, hopefully. Okay, let's move on to a couple other examples here with this, okay? Let's do this. This example 2 is just like example 1, just with a different function. So I'm giving you this. If you just write down this function right here, you'll be good. And then we can kind of write down the details here, okay? All right, so we're going to write the equation of the line that represents the linear approximation. Okay, so first of all, let's go ahead and write down that. We have L of x. Okay, that's the linear approximation. That's going to be f of a plus f prime of a, and then x minus a. Okay, like that. You can do it that way, or you can just say, I need to find the equation of the tangent line at that point. Okay, well, a is pi over 4, so let's go ahead and write it like this. That would be f of pi over 4 plus f prime of pi over 4, and then we would have x minus pi over 4 like that. So we're using pi over 4 to approximate what f of 7.5 is. Okay, so that's how you want to start the problem, is like that. Okay, well, let's do f of pi over 4. How do you find f of pi over 4 in this problem? You evaluate the function, right? What's the function? Sine of x. So pi over 4 is a unit circle thing, so that's why I chose that value. So you're going to do the sine of pi over 4. What is that? Square root of 2 over 2. Okay, that's the easiest one to remember. Good. Okay, so we got that. So what's going to go in there is, that's going to be square root of 2 over 2 goes there. Okay, now you need to do f prime of x, because you have to find the slope of the tangent line. Okay, what's f prime of x in this problem? Cosine of x, good. Simple derivative. So now you're going to do f prime at not square root of 2 over 2, I'm ahead of myself, at pi over 4, like that. So we're doing f prime of pi over 4. So that would be cosine pi over 4. Tell me what that is. It's root 2 over 2 also. On a unit circle at pi over 4, that's the point is square root of 2 over 2 comma square root of 2 over 2. Okay? So that means this value is going to also be square root of 2 over 2. Then we have x minus pi over 4 like that. Okay, I'm just going to write that, keep bringing that down as L of x like that. So if you were doing the slope of the tangent line or the equation of the tangent line like you've done all semester, you'd be at the same place here. Okay, so that's going to give L of x is equal to root 2 over 2. Go ahead and do the distributive property here. So that's going to be root 2 over 2x and minus root 2 times pi all over 8 if you multiply that out. And that's good enough. You don't have to really collect the like terms or anything unless you want to. That's good enough. So you could leave it at that point right there for your equation of your tangent line if you wanted to, okay? Or you could add, these things right here are actually like terms, so you could also go ahead and add those together. Let's go ahead and just add that together, I guess. We might as well, okay? All right, so let's see. We have square root of 2 over 2. Oh, didn't I say 8? Sometimes I say and write the wrong thing. My brain doesn't multitask very good, I guess. Okay, so we have that. All right, so let's do root 2 over 2 minus pi root 2 over 8. Well, all you're going to do is just get a common denominator. Okay, and this to me is, you don't necessarily have to do that. But if you needed to do this, this is what you would do. So you get a common denominator, and that would be 4 root 2 minus pi root 2 all over 8. If you added those together, you'd keep the denominator 8, and then you'd combine the numerator. You could factor a square root of 2 out if you wanted to. I'll go ahead and do that. So if we do that, we'd have root 2 and then 4 minus pi all over 8. Okay? So you could, I wouldn't care if you left the answer this way, like I have here, but just in case, because sometimes my math lab is going to direct you to go a little further, you'd have root 2 over 2x, and then the result of the like terms is plus root 2, 4 minus pi over 8. Okay, so that should be your answer to part A. That's the linear approximating formula right there. Okay, is there any question on anything I did there? Okay, I gave you everything you needed. I gave you A, okay, gave you the function sine of x. You're finding the equation of the tangent line. Okay, now a graph on this, if we do a graph, let's go ahead and do that on the calculator. I wouldn't expect you to do this without a calculator because that's a pretty messy linear approximation. You could get decimals and stuff on that. So what we'll do on this one is let's put in, let's see, we're interested in f of 0.75. So let's go ahead and put in these two things. Let's put in sine of x. Make sure your calculator is in radian mode when you do this because we don't want to be in degree mode. So we're going to graph that out. And since we're doing f of 7.5, we'll do the x values around that value. Okay, now when you put in this tangent line right here, you got to be really careful about how you put this in. You would have to go parentheses, square root of x, and then get out of that, and then divide by 2 before you put in the x. So that must be in parentheses because it has to calculate that before it multiplies by x. So that's important. So you have to put that in like that. When you put in the next part, you should be able to just do this like this. You could go root 2. Did I do something wrong?
Yeah, it's not square root.
Oh, I know what I did. That's root 2 over 2, right?
Yes.
All right, thank you. You guys are very observant. Okay, now let's go to the next thing. Okay, so now I've got root 2. You don't really need parentheses because you're just dividing by 8. Then you could go 4 minus pi. Okay, like this. Okay, then divide by 8. All right, and visually this should look right to us. If we did everything correctly, visually we're going to be good. I hope we did everything right. Okay, so I'm going to slide that over like this. If you need to get that put in, I'll put that over there. Okay, for a window, let's do 0 to 1. The reason I'm doing that on x is because you're interested in f of 0.75. So 3/4. So you want to just make sure that visually you can see what's going on at f of 0.75. Okay? And let's see, the sine graph has a max of 1, right? So let's do something for the y, let's go like -2 to 2. That's one way to do that. There's other ways. I'm just thinking about the sine has a max of 1 and a min of -1. Okay, so I'm going to do that like that. You'll slide that over there if you need to put that in. And let's see what we get here. Okay, I think I'm in degree mode. That's why it's doing what it's doing. Okay. Now there's my function. That could be right though. Let me check. Yeah, I'm in degree mode. That's what I thought. Okay, so get in radian mode. Okay, now we try again. Okay, so we should see a part of the cosine graph coming out. And if we did that tangent line correctly, I was a little suspicious about that because the algebra was kind of complicated. Does that look like it's a good tangent line? Yeah, okay, that looks good. Okay, so you've kind of got something kind of going on like that. I'm probably going to go ahead and maybe change my window now for the y's to, you don't have to do this, but you'll probably see it a little bit better if you go 0 to 1 on y, okay? But I just want to kind of do that to check my tangent line. You can do this on homework. If you're not sure if your tangent line is right, that equation, just graph it and you'll visually see if it is. So now it looks better, doesn't it? Okay? All right, so that would be a good graph. I wouldn't expect you to do a graph on this any other way to just get your calculator out and let the technology do that for you. Okay, so what you have basically here is sine of x, and then this is your tangent line like that. Okay, now we're going to do the linear approximating formula, and then we'll do the error to finish this up then. Okay? All right, so let's see. On part C, what we want to do is use the linear approximation to estimate the given function value. What is the given function value that we are interested in? 0.75. Okay? So what you're going to do is, you're going to do this on the calculator, you're going to do L of 0.75. So you have two choices. You could either plug that 0.75 in here and do your calculator, or since we've already graphed it, the reason I'm going over the graphing is because when you're doing your homework, just do it this way. Don't waste your time. I wouldn't expect you to do this any other way except to do your calculator, just to get an approximation. So what I'm going to do is I'm going to trace not the function, I'm going to trace the tangent line at 0.75. So this is something you want to learn how to do. So if I type trace, you don't want to trace on the sine. You want to use this up, down. You want to get it on the tangent line. So you can do that up, down. Now you type in trace 0.75, and the calculator is going to do all the dirty work for you, which is what you want. So what you get is that linear approximation is about 0.6820765. Okay, you guys see what I did? Just trace. And see if you graph, that way you're telling visually that your equation of tangent line is right. You see what I mean? And then you're just saving time by doing it this way. What do you think? Okay, your other choice is to just take your calculator, plug in 0.75 and work that expression out. Okay, more time serving that way. Okay, so that's your approximation. Part D, what we're going to do is we're going to do the error. So when you do the error, what you always do is you always do the estimate minus the exact. It actually doesn't matter which order you do that in because you're going to do the absolute value anyway. And then you compare that to the exact, and then you change that to a percentage. So here's what I'm going to do. While I'm at it, I'm going to go ahead and get the exact answer too. And I'm going to use my calculator to do that. So the exact answer is going to be f of 0.75. Just trace on your calculator. So when you trace the exact answer, which curve do you want to be on?
Sine.
The sine, right? That's what we're trying to find. So make sure that you've got the sine highlighted. Now put in the 0.75, and then we'll record what that is. So that is about 0.68163,876 like that. Okay, so now we're ready to get everything put together. Okay. All right, so notice that these things were pretty close to each other, so it looks like we got a pretty good approximation of the function value. So what we'd have is the estimate was 0.68. Was the first one we got from the linear approximation. That's 0.6820765. The exact is what I just traced out. That's 0.68163,876. I would use all the decimals that come out on the calculator, and then compare that to the exact. Okay, do that on your calculator, then change it to a percent. That's what you got to do to complete the problem. Okay. All right, so I'll just do that kind of like this. So I'll do the estimate, 0.68206765, subtract the exact, 0.68163876. Okay, hopefully I got that right. Somebody can check my work. Now that's scientific notation, just leave it the way it is. Now divide by 0.68163876 like that, and that'll give you scientific notation again. So use a positive answer. That's 6.4 times 10 to the negative 4. Okay? Now, what does that mean? What does negative 4 in scientific notation tell you about the decimal? You need to move it to the left. Okay? So what you'd have really is 6, 4, and just count 1, 2, 3, 4. So that's really this, right? Okay? So what is the percent on that? Okay, change it to a percent, you multiply by 100 or move the decimal back 2 this way. So the error would be 0.064%. That's it. Okay, so all you're doing with this error approximation is taking the estimate you got minus the exact, that ratio, and comparing it, and then you change it to a percent. So that's very accurate, isn't it? Okay, and in this case, we had a very, very accurate linear approximation. Okay. All right, does that make any sense? Tell me. Okay, good. Is it getting better? I kind of sensed for a while it was you weren't understanding a word I said. I don't know if I was right or not. Okay, let's do 2 more things to finish this up. This is kind of what you're getting at here, is with linear approximation. Let's do these last 2 examples, and that'll finish this up here. Okay, so what we're going to do on this is the 2 problems I want you to know how to do are the ones that I just did, and then something like this. You know, for testing purposes, this is kind of what I'm looking at on the calculator part of your exam. So you're going to approximate the cube root of 64. So that means that the function you're working with is just going to be the cube root of x. Remember we did the square root of 26 earlier, we used square root of x. That's what you're going to differentiate, okay? Now, what you want to do is you want to choose a value that produces a small error. Okay, some numbers we know the cube root of are, one thing you know a cube root of is 8. Another one you know is 27. What's another one? 64. That's probably the best one. How come? Because it's so close to 65. Agreed? Okay, if you used cube root of 8 or cube root of 27, you would get a linear approximation, but it would have a bigger error. So you want to get as close in as that you can. So what we're going to say is A is 64. You want to use something you know. Okay, that's the idea. Something that's close. All right. Okay, so what we're going to approximate is we're really going to approximate f of 65. Okay, is what we're ultimately going to do, is find the cube root of 65. That's what we want to find. Okay, well, let's write down the formula. So L of x is f of a, then it's plus f prime of a times x minus a. Okay, refer to the formula or do the point slope formula, either way. Okay, so let's see, we're doing f of a. So let's see, a is going to be 64. So we're going to do f of 64. Then we're going to do f prime of 64. And then we're going to do x minus 64. We want x to be a variable because we want an equation of a tangent line. That's the idea. Okay? All right, so let's see. If we do f of 64, well, the function is cube root of x. So what are you going to do? You're going to do cube root of 64, right? Okay, we use that because we know that. Okay? Now we need to work with the derivative. So if you work with the derivative, let's see, f of x, the cube root of x, you want to write that as x to the 1/3. Then you want to do your derivative, correct? Just basic power rule stuff, okay? So we got to do f prime of x, then evaluate it at 64. All right, so what's f prime of x here? 1/3 x to what power? Negative 2/3, right? Okay, everybody got that? Okay, write it like this. This is 1/3 x to the 2/3, like that. Okay, And then you can write that if you want to. You can change this back to a radical, because you're going to need to do this to evaluate this anyway. So you'll have 3 times the cube root of x squared. Okay, like that. Okay, so that's derivative. So why are we doing the derivative? So we can do this piece of the formula right there. So let's go ahead and just write that out. We're going to have 1 over 3 times the cube root of, okay, and then what we're going to have on that is a is 64. So we're going to have 64 squared like that. Okay, so you're going to plug that 64 into your first derivative. And all that's doing is giving you the slope of the tangent line like that. Okay, everybody with me so far? Okay, everybody understand why I chose 64? Okay, that's a key, all right. So let's push on and see what we got. We're almost done here. So cube root of 64, what's that? 4. Okay, let's look at this thing over here now. And you could go to your calculator, but you don't have to go to your calculator. What you're doing is you can think of this as a cube root of 64, then that whole answer squared. That's the way to look at it. You might think, well, I need to square 64. No, you don't. You can do it this way. So if you did it this way, then what's the cube root of 64? 4. And then what's 4 squared? 16. You can do it in your head. So you got 1 over 3 times 16. So that's 1 over 48. Okay, so that's what you have there. Okay, and you'd want to do that. You'd want to get that precise answer. So that's what the value of the derivative is. So that's giving you the slope of your tangent line. And then you're going to do x minus 64 like that. Okay, so that's really what L of 64 is. Okay, that's L of x. I'm sorry, that's the general formula for L of x. Okay, now you can simplify it if you want to, but you don't have to. If you want to take your time to multiply it out, you can, but there's no need to do that because all you're doing in this problem ultimately is what? L of 65, agreed? Why not just plug it in now? It's easier. Okay, so all we got to do is take this thing right here, and where you see an x, plug in a 65, then we'll have a good answer. So that's going to be 4 plus 1 over 48 times 65 minus 64. So that's going to give 4 plus 1/48 times 1. So the answer is 4 and 1/48. And you can write it that way, or you could go ahead and write it as a decimal if you wanted to too. So if I just do 4 plus 1 over 48, I'll just maybe round that to a few decimals. Okay, that would be about 4.02. And the 3's repeat. You can round it to whatever you're supposed to round it to. That's it. So that's your linear approximation. Okay. Now, when you're doing homework on this and everything, like if you were doing a quiz or something, you want to find out if your answer makes sense. Well, first of all, is that a pretty sensible answer? The cube root of 64 is 4, right? So we expect to get a slightly bigger answer. So that's pretty logical. What do you think? Okay. And you're better off on this problem to plug it in there than to waste your time multiplying it out and writing it as y equals mx plus b. What do you think? That's easier, so do it that way, okay? All right, let's do one more of these and see if we kind of got the idea here, and that should be enough here. Okay, so we're going to do f of x is going to be the cosine of x. This time we're approximating a cosine. 31 degrees is not one of your special angles on a unit circle, right? What would be a good angle to use? Unit circle, what's good? 30, right? You know what the cosine of 30 is. So we're going to use A as 30 degrees, just like the last problem we used 64. Does that make sense? Get as close as you can. You'll find on your homework, most of the time, they're going to give you something that's one or two units away from the good number. Okay, that's the idea. Okay, so let's write down the formula again. So L of x is equal to f of A, and A is going to be 30, something we know, plus f prime of A, and then x minus A like that. Okay, so let's go ahead and just kind of figure out everything on this then. Well, we need to do the derivative. So f prime of x, what's the derivative of the cosine? Negative sine x, good. Okay, so we just plug everything in then. So we're going to have L of x is equal to f of A. Well, that's going to be the cosine of 30, because A again is 30. Then f prime is negative sine And then again, use 30 degrees. Then you have the x. X is a variable. You want to leave that alone. And then a is 30 degrees like that. Okay? Now you can do this in either radians or degrees. Okay? It's your call. The reason I'm leaving it in degrees is because they gave you 31 degrees. There's no need to change this to radians because when we get the formula in terms of degrees, it'll work out fine. Okay? All right, so let's see what we know. Let's see, on a unit circle, let's see, 30 degrees. What's the point on the unit circle at 30 degrees? Square root of 3 over 2, 1/2. That's pi over 6, right? Look it up if you have to, or just create it as you go. That's what you want to learn how to do. Okay, so what's the cosine of 30? Square root of 3 over 2. Okay, get that from the unit circle. Now you're going to have minus, see that comes down. The sine of 30 is what? 1/2. Then you have x minus 30 degrees like that. So that's it. Now you do not need to multiply that out. There's absolutely no need to do that because the problem, what you're doing is you're doing L of 30. Okay? All right? Or I'm sorry, L of 31 is what you're trying to find. You're trying to find the linear approximation of 31 degrees. Okay, everybody with me okay? Okay? And this is not too hard, okay? This one's got nice simple derivatives, and that you like it when that happens. Hey, just plug in 31 now, okay? So you're going to have root 3 over 2 minus 1/2, 31 degrees minus 30. So notice you're going to get, it looks like, square root of 3 over 2. Then you're going to have minus 1/2 like that, okay? And then if you go through and do that, now let's use a calculator on this. And if we do this, let's see, I want to go back to degree mode on here. Oh, the battery's going dead here. There we go. So you want to go ahead and get that put in. What I'm going to do in degree mode is I'm going to just kind of see how close I am here. Okay, so let's see. If we do and I'm going to get the exact answer. So what are we doing in this? We're doing the cosine of 31. So in degrees, if we do cosine of 31, okay, we're going to have about 0.85. Okay, and then if you do this, and you may have to be in radian mode. Let me think about this for a second. Let's just, because we know our answer is going to be close to that. So if we go square root of 3 and then divide it by 2 minus 1/2, that gives us nonsense. That's what I thought. Okay, you need to be in radian mode because when you're doing an exact calculation on this, degrees is not a real number, so you need to be in radians. So what we're going to do is you can go ahead and do the problem this way, but what you need to do is convert 1 degrees to radians. So the way you do this is you just do 1 degree times pi over 180. Now if you do that, then you'll be in good shape. Now you could have done that at the beginning of the problem if you wanted to, okay? So let's just do square root of 3 over 2 minus 1/2, and then 1 degree is pi over 180. Okay, now let's do it on the calculator and see if we're pretty close to 0.85. Okay, that's what I thought. You're okay to get the linear approximation formula in degrees, but you do have to go to radians to get a sensible answer because you want a real number. Let's see, let's go square root of 3 now. And let's see, get that put in, and then divide by 2. Okay, and really what you're going to do on this is you're going to do minus pi over 360. If you multiply that out, you would do pi divided by 360. And if you do that, okay, now we're getting a pretty sensible answer, see. And the pi over 360 comes from here. So that would be approximately 0.8572987575. Now, if I did the cosine of 30, now in radians, the cosine of 30 is 30 is pi over 6. So I'm going to do that just to compare how close we are. Okay, is that right? Oh, we're doing 30, I'm sorry, we're doing 31 degrees, I'm sorry, okay? All right, so it would actually be if you went back to radians. I think I did that in degrees a minute ago. If I did cosine of 31, I had 0.85, so you're actually very close. I like that. So that's the idea. This is more of an exact answer. If you did cosine of 30 and 31 in degrees, you'd have extra decimals, but you're actually very accurate on this one. That's the idea. Okay, does that make sense? Okay, so just kind of close off one more time. If you do, let me just go back and show you this one more time. I'm going to go back to degree mode here. And if I do the cosine of 31, okay, that's going to be, that's the exact answer. This is our approximation. So if you look at those two things, they are awfully close. Okay, so this will kind of begin to get you an idea leading up to how your calculator would end up ultimately getting a more precise answer. So that's kind of the idea that you're getting into. Okay, do you guys understand what's going on and think you can do this okay? Okay, it's not that bad. It really, really isn't. And I've kind of given you the basic things that you want to know how to do. It's a little abstract.